Hope everybody is good. So we go to our lecture in the name of Allah. If you have any questions, please let me know. We will go a little bit faster to cover the materials because you have also a midterm on 19. Yeah? I have written for you. So June 19th, Monday, 2 weeks from now. 2 weeks from now. So hopefully either today or the next lecture, we cover the material of chapter 2. And this is it is for the midterm. So the midterm would be at the end of these slides in the chapter 2. So hopefully we could finish it today or maybe Friday. Okay, I guess we were here. So any questions? What did we do up to now? We talked about instruction set architecture. And why did we do that? Because defining the instruction sets is the main thing for designing the CPU, the processor. When you want to have a processor, you need to look at the instruction set and try to design something that could execute those instructions. The instructions are the interface between software and hardware. And we now designing the instruction set. Actually, we don't design, but we just present. If we had time, then I could go through each of the decisions that we have made. Let's say 32-bit registers, 32-bit instruction length, any of the decisions any of the things that I represented for you, we could have discussed with each other and to see what would be a good design for instruction set. But now, instead of that, I just present for you and I will tell you, this is the design of a modern RISC architecture. Is it the best? No. Is it? Could you do something better than that? Yeah, you might be able to do that. But the main important thing is that it depends on the applications that it wants to execute. So you have something as benchmarks. You try to execute those benchmarks on the architecture and see if it works. And if it works better than the other architectures, then it means that it is better. Otherwise, we don't know. So this is not something that is a mathematical point that 2 + 2 = 4 and that's it. No, it is design. In design, you have so many choices, so many options, and you try to design the best one according to the criteria you have, the constraints that you have, the resources that you have. So that's the thing that we do in engineering, and it is the same thing. So up to now, I told you, we have two kind of formats for our instructions. One of them are R formats. In R format, you saw that there is opcode, which is 0 for now. Then we have 3 registers. Then we have shift amount, 5-bit, and then we have function code. 6-bit, 555, then 5, then 6. The total would be 32 bits, like any other format that we are going to discuss. The idea was to make it fixed length instruction, which will help us a lot when we are going to design our processor, because the processor should be able to decode the instructions and to execute them. So if they are fixed length, you will see later when we are going to design the processor that how it helps us a lot. So this is the first one. arithmetic instructions. We had arithmetic instructions like add, subtract. We had logic instructions like and, or. So they were all in R format when you are having two operands as register, two register operands as the source and one register operand as the destination. Then we had I format, immediate format, which part of the instruction contains a fixed, a constant, an amount, an immediate amount. So, and that was how many bits? 16 bits. So you see, in these instructions, we are already lost 16 bits, and only 16 bits left for us for other things like opcode and operands that we would like to have. And we saw that, how did we manage that? We had an opcode of 6 bits, then we have two registers, 5 each, and then we had immediate. 6 plus 5 plus 5 is 16, and then 16 bits for the immediate value. Okay, so that was the I format. And again, here we had arithmetic operations like add immediate. We had logic operations like and immediate or immediate, signed, unsigned, and these things we could do that. So you, from now on, you should be very careful when you are looking at the numbers. Is it signed or is it unsigned? There are places that when you look at them as a signed value, it is different than when you look at them as an unsigned value. Sometimes they are the same. For example, in logic operations, there is no sign. So you just add bit by bit together. But when you are doing add, when you are doing comparison, two numbers, you compare two numbers, which one is bigger, which one is less, which one is greater, then sign is important. We are looking at them as unsigned or signed. So this is also, we have talked about it. Then we also talked about memory operands. So up to now we had register operands, we had immediate operands. The third one is memory operands. For memory operands, in MIPS, we have been using base and offset address. The base would be in a register, and the offset would be an immediate value, a constant. So again, memory operations like load and store, they go in which format? R or I? I, because they have a fixed amount of offset, which is 16 bits. So memory operations like load, like store, they go to I format, and they have register as the base, and then offset, immediate as the offset, and a register to, let's say, load it or store it. Now we are going to talk about other kind of instructions, which we could call them as control instructions. With control instructions, we mean that when you have a program, the program typically starts from a position, executes this instruction, and then go to the next instruction, and then go to the next instruction, and then go to the next instruction. This is the typical path of executing a program. But sometimes we will change these paths and we go somewhere else, like jump to somewhere and then coming back. Like calling a function and then from the function we return. Like having a branch and a condition. If this is greater than this, do this, and if not, do that. So you have written programs, yeah? You have written C++. What kind of high-level language did you work? Python. So you. But in the university, which course? You had Python course or you have Python? So any high-level language is okay. Python, C, Java, C++, any kind of high-level language. When you write your program, there is something that you do it one by one, and then there are something that change the typical path, like jump, go to, for example, like loop. You have a loop. You start something and then you're going back. Something's then going back. This is a loop. So these kind of instructions, they control the path, the execution path of the program. Now we look at these instructions. First, we start with conditional operations. You want to go to an instruction based on some conditions. As, for example, in C, you write if A greater than B, then something, else something else. That's how you write in C. This is the first one. Look at this instruction. It's very important that you get familiar with this instruction. Because have you ever worked with assembly language before? No assembly. So you are all in high-level language. Now we are going to assembly level, in the low-level language. So this is low-level, and it is a little different than how you write in high-level language like C, Python. So here, look at this instruction. Again, this instruction, like other instructions of MIPS, has a very... Oh, let me... Okay, has a very regular format. The format again has two register operands and then a constant, an immediate value, which we will talk about this. What is it? This instruction says branch unequal. Branch unequal. If RS, the value of register source, one of the sources, is equal to the value of register RT, then go to this label, this location, which we will see later. What does it mean? So go somewhere. So it's like writing if in C program. So if RS equals to RT, then branch to an instruction which is labeled L1. Or the other instruction is branch on not equal. If RS is not equal to RT, then go to L1. And then what about else? So if it is not true, what happens? In assembly language, we don't have else. We just have a condition. And if the condition is true, which we call it taken, which if the condition is taken, is a taken branch, then it goes to that location. Otherwise, the regular path of the program, which is the next instruction. So we were executing instructions one by one. Load something, store something, add something, so one by one. Then we reach to branch instruction. Branch unequal S0, S1 to L1. L1 is the label, we will see later. If the condition is true, then the program goes to L1. Otherwise, the next instruction. The next instruction is executed. So in assembly language, we just have a branch, either it is taken or not taken. If it is taken, it goes to that location. If not, next instruction is going to be executed. And then again next, again next, again next. Even if it is taken and it goes to another place, then this instruction is executed, then the next instruction, until we reach to a branch, another branch instruction, which again changes the path of the execution. So if they are not equal, then jump to something. So this was the first kind of conditional operation which changed the path of the execution. The other instruction is jump. So it is another kind of changing the path. It is the control instruction that changes the path of the execution, and it is unconditional. No matter what, when the program reaches this instruction, it goes to L1. Wherever L1 is, you will see what is L1. Now you might have not an idea what is L1, what is a label, but we will see an example. We will see examples. So unconditional jump to that. So if you look at these instructions, the first two have operands and also have an immediate value. RS, RT, L1. L1 is a constant number, like 10, something. So you could guess that these two instructions are which format? Again, immediate format. Again, immediate format. Because they have two registers and one immediate. And from this, you could find out that the immediate would be how many bits? 16 bits. So look at it. Think here, when we decided to keep every instructions as 32 bits, we are doing some compromises, and we should stick with it. We know that it is not ideal, it is not perfect. The perfect would be what? What is the memory locations? I told you before, I guess. Each memory location, not the content, has 32 bits. So you could have, in MIPS, you have registers, you have memory addresses from 0, let me write in hex, 0, 0, 0, 0, 0, 0, 0, 0. This is the lowest address of the memory up to F, 8F, 32 bits. This is the highest address of the memory. So ideally, we would like to have some kind of address which is 32 bits. But what do we have here? This is an address that we have to go there. So this is an address, and it is only how many bits? 16 bits. So this is a compromise. So what do we do? It means that we cannot jump to wherever we want to go. Yeah, it means that. But we could think about it more. And the idea here that designer thought about this, and they say, if you look at the programs, the benchmarks, usually we use branches for loop, for if something doing something. These are the branches. And usually the target address that we would like to jump to that location is close to the location, the instruction that we are doing the comparison. If this is equal to that, jump somewhere. And that place is usually close to the other location. So what do we do here? If they are close, then we could listen to this very carefully. How did they design? How did they design the processor? So if this is the case, we consider this immediate value as a relative address to the place that we are. So if we are here, and then we would like to go to this location, which is only 20 address after this place. So we just put 20 here. And we solve the problem as 32 bits. We don't have 32 bits. We only have 16 bits. But with these 16 bits, as considering the address as the relative to the place that we are at this time, we solved that problem almost. I am not saying that we solved it completely. If you look at the benchmarks, there might be less than 1% that you need to branch to somewhere which is far from this location, which is more than 16 bits, and this 16 bit is also signed value. It means that you can, from here, you can go in a forward direction, or even you can go in backward direction. For example, in loops, we usually go back to do something and then go back again. Do something, then go. Okay, did you see how they think, how they think about this, how they designed the processor? This L1, the value, the immediate value that we put in the instruction, which is 16 bits, would be a relative, an offset to this current position. So it has been solved a lot. The next thing, when we come to J, to jump, so this is not a branch. This is something that we would like to go wherever we want. This is not a branch. If it is closed and we want to do that, maybe we could do some branch with some condition that it is always true. For example, we write branch unequal, branch unequal 0, 0, and a label. So this is always true because the register 0 is always 0, the register 0 is always 0, so they are always equal. So this will always go to this location if you want to do it relatively. But we want to have something which we could address whatever we want. We are at some positions, we would like to go to another location of the memory which is not close to that. We just want to go to another module, for example. What to do? So we need this instruction should be absolute location, not relative location. Okay. So if this is absolute, how many bits L1 does have? Who could say? Because the whole instruction is 32 bits. And for sure, you know that L1 is not 32 bits. You know for sure. It cannot be 32 bits because there is something for opcode. At least opcode, we have some for opcode. So the designers thought about this and look at how did they decide. Again, they started a new format. So we have three kinds. I told you before. Three formats: R format, I format, and J format. In J format, we have an opcode, which is 6 bits, and then we have the constant, the value, which is how many bits?
26.
How many? 26 bits. So instead of 16, we have reached to 26. But it is not enough still, because we want 32 bits. It is not enough. So what to do? There is still problems. One solution that you might think, and if you have projects for doing some kind of design, processor design, instruction set architecture, you could try to make the opcode for 2 bits, and then you have 30 bits. And 30 bits is good. I will explain for you why 30 bits is good, and it's enough instead of 32 bits. Could you guess? We really need 30 bits, not 32 bits. Do you know why? Any guess? The instructions are how wide? Each instruction is 32 bits. Yeah? It's 32 bits. So each instruction is 4 bytes. And I told you before that we are byte addressable. Each byte has an address. Address 0, 1, 2, 3. Together, they are a word. Then address 5, 6, 7, 8, they are combined and they they form a word. And we are sure that each instruction is 4 bytes, 32 bits. So even if for data we were thinking of byte access, half word access, in addition to word access, which is 32 bits. But in instruction, we are sure that it should be word access. Each instruction is 32 bits, just nothing else. Did you follow what I said? I said, okay, even if for data we need some kind of mechanism to be able to access bytes, even location 0, 1, 2, 3, we should be able to, for example, load a byte from location 3. Because we are byte addressable. We should be able. We cannot access a word from location 3 because it is not aligned, and it should be aligned. But we could have 1 byte from location 3, 1 byte from location 2. But even in data, we have some kind of byte operations or of half word operations, 16 bits. In instructions, we don't need that. It's always 32 bits. Since it is always 32 bits, it means that what would be the address of the instructions? 0, then the next one. Which would be the instruction, the next instruction? If it is 0, the first one, the next one would be 4. The next one would be 4. It cannot be 1, 2, 3. The next one would be 4 because it is 32 bits. 0. The next instruction is 4. The next instruction is 8. The next instruction is 12. So if you look at the instruction addresses, they are always have 2 zeros of bits because they can divide by 4. So all of the time they have 2 zeros at the end. Yeah, 0. Let me write it for you. Address 0. Address 0 is 0, 0, 0, 32 zeros. Address 4 is 0, 0, 0, and then 1, 0, 1, 0, 0. Address 8 is 0, 0, 0, and then address 0, 4, 8. 8 is this. Address 12 is again 0, 0, 0, then 1, and this. And so on. So if you look at here, always the last 2 bits, the least significant 2 bits are 0. It's obvious because they should be divided by 4. So they should be multiplied of 4. So always it is 2 zeros. So we don't need the 2 bits, the 2 least significant bits. So if we have a number of 30 bits, that would be enough for us. 30 bits, then we add also 2 zeros at the end, then we have a 32-bit address, which is okay. Again, I am saying, MIPS didn't go this way. MIPS selected the opcode of 6 bits, not 2 bits. But I was telling you that as an engineer, you might have designed a processor, even if it is 32-bit fixed instructions, you could have assigned 2 bits for J format, 2 bits for the opcode and 30 bits for the immediate. So this is also, but it has some kind of consequences that I am not going to talk about it later. You think about it. Maybe that would be a good question for your exam. That what happens if we do that, and does it work or not? So MIPS, what did MIPS do? MIPS, let's go back. MIPS for this kind of format selected 6 bits of opcode for jump and similar one. We have 2, 3 instructions which are like jump, and then 26 bits for the address that we would like to jump. Again, we are short. 26 bits. Even if you put 2 zeros at the end, because I've told you that there is always 2 zeros at the end, we have 28 bits, but we needed 32 bits. What to do? Again, the designers thought about it and they said, okay, we cannot do it. It is 32 bits and we cannot provide it. But for making it this something happen, because it needs to work, they borrowed 4 bits from the current location. Here, I told you from the current location, we use an offset to go to somewhere. Here, in this format, they use the current location and they get 4 bits from the location, the 4 most significant bits. They put it here, and then they put the next 28 bits. The next 28 bits, 26 bits is here, 2 bits is 0. Okay? Any questions? Did you follow? No? Again, do you want me to take them? Our address to jump should be 32 bits. Okay, is it okay? Everybody? You know why it should be 32 bits? Because every address is 32 bits, and the locations are locations in MIPS. They have an address of 32 bits. It's the design, 32 bits. With 32 bits, how many memory could we have? 2 to the 32 is how much? 2 to the 30 is gig. 2 to the 4 is 4 gig. So we have 4 gigabytes memory in MIPS with 32 address bus. If your address is 32 bits, then it means that you can have 2 to the 32 locations. So this is the MIPS, 4 gigabytes of memory. That's it. You are now looking, you are now seeing that there are some limitations, some constraints with this design. But I've told you before, there should be something, but instead we are going to have a very effective and high performance processor because we had some compromises, we had some limitations, we had some regularities, we had some simplicities. These things that we taught, there were 4 rules for the design. We try to make common case fast. We don't care about not common cases. So these things that we try to design the MIPS with these rules, this is the result. So that's it. 32-bit address. Okay. I guess. And then, okay. So we needed 32 bits. But here in this instruction, jump L1, this instruction has 6 bits as opcode and 26 bits as the value that we would like to use it as the address to jump. 26 is not 32. So what to do? The designers decided to do this. First, they have concatenated 2 zeros at the rightmost of the address because it should be always 2 zeros at the end. So this is, now we have 28 bits. We are 4 bits short. The 4 bits short that we have, they got it from the 4 most significant bits of the current location of this instruction. Let me say, it's called PC, program counter. Program counter is the register which points to the instruction that it is going to be executed now, currently. Then, after it is executed, the PC increments by 4 to the next instruction, until we have some kind of branches or jumps, which PC would become that. Instead of just adding 4 to PC each time, it goes to somewhere else. So 4 bits from PC, 26 from the immediate value of here, and 2 bits of 0, they form a 32-bit address for location of jump. Okay? Better? Okay. So let's do some examples. In our course, you need to write assembly programs because later you are going to design the processors to decode these and then execute it. So you have to know how to write the programs. And later in next chapter, we are going to design the processor to execute these instructions. So let's start. This is an example. In C, for example. In C, write if I equals J, then F gets G plus 8. Else, F get G minus H. Okay? How do we write it in assembly? We have to use branch equal or branch not equal. Using that, we should be able to write something like that. So, the MIPS that I suggest, it is not unique. You might write some another way. But this is what I start with it, and let's see if it works. So this would be, let me see if I have it here. Okay, I have it here. Yes, here, I guess this is the one. Let me see if this is the one. Always use Notepad. Okay. Branch and not equal, add. I guess this is the one, yeah? I haven't written that's the one or not. Let me see what did I write and then. Okay, what I do here, let's say F is in S0. G is in S1, E, F, G, H in S2, F, G, H, I, F, G, H, I, A, B, C, D, E, F, G, H, I, G, H, I is S3, and J is S4. Let's say that we have put our variables in C in these registers. So how they come into the register, they don't care now. Somehow, S0 is F, S1 is G, S2 is H, and so on. Now, let's write the program. What do we want to do? We would like to compare I and J. It means S3 and S4. Okay, let's compare it. Branch are not equal, S3 and S4. And then if it is not equal, it should go to some place that we subtract G and H and put it in F. If it is equal, then we have to add G and H and then put it in F, okay? So here, I am saying that for the time being, just look at this. This should be a location of the place that we do this. Okay, so let me write else. So this is else. When you want to label a location in your code, you just put a location, put a label, and then colon. For example, here I put else. You could put anything. You could put anything you want. It is a label. It doesn't have anything to do with assembly, with the instruction sets. The instruction sets are here, but this is the label. I just put else. You could put something else. For example, another pass, another place, whatever you want. This is the label. And then I have to put colon here. So the assembler, the compiler, when looks at your code, when it sees this instruction, it finds out that, okay, you want to go to this location when it is not equal. So it calculates this location and puts the immediate as something that goes here. We will see it right now. Okay. So if it branch not equal, if S3 and S4 are not equal, then jump here. And in here, we are doing subtraction. G and H are subtracted, and then put it in F. F is S0. Okay? So if it is not equal, then I told you what happens. Then the program goes to the next instruction. So we have to put, so this is the assembler calculates else location and it puts it there. We will see it. And this is the other pass. If this is not correct, if this is not equal, then it goes to the next location. Here we don't have else. If not equal, go here. If not, If that branch is not taken, then the next instruction should be executed. Okay, so this is the next instruction. That's it? Are we done? Finish? If anybody says something that why it is not complete, then he or she will get a point. Yes?
Should we jump so we don't go to the else?
What happens if we go to else?
It will subtract.
Okay, so what?
We don't want that.
We don't want that because we want just to put add. What's your name?
Anas.
Anas? Anas? Okay. I have to put a place in the site that you post there that you answered something that you get a point. Just remind me later. So what is Anas is saying that, okay, if this is the program that we have written up to now, let's see what happens. We have S3 and S4, which they are equal. Let's say they are equal. So if they are equal, so this branch is not taken. Branch not equal, we say. This branch is not taken. So the program, execution of the program goes to the next instruction, which add it. So up to now, everything is okay. We add G and 8 and put it in F. And then, after executing this, what happens? The PC gets the next PC increments by 4, and the next instruction is this. So it comes here, and here we subtract S1 and S2 and put it in S0. So everything is ruined. Everything is overwritten. So we had F, G plus 8 here, and then again we came here and made F as a subtraction of G and H. Okay, so that's not good. So what should we do? As he suggested, we have to put some jump here, so we don't go to this location. We go to the rest of the program, whatever it is. So here we say jump exit. For example, I put the label exit. You might put continue. You might put the rest. You might put the program, whatever you want. So this is the exit label. So again, if they are not equal, the branch is taken. And if the branch is taken, it goes to here. If they are equal, so the branch is not taken. So the next instruction is executed, and then the next instruction is J, and it comes here. So in both directions, we reach here, but with the correct path that we wanted to do. Okay, let me, I hope this is something like that. It is, it's similar. So let me work with this. So going to our simulator, where is that? Content, simulator, where is simulator? Here. So this is our simulator. So I write this program that I've told you right now. So I have already written, so I open it for you. So here, this is the same program. I guess it is similar, I'm not sure. Yes, some kind of similar. So here you see, I commented this line, the line that we were talking about, if it should be there or not. And let's see what happens. What did I put? I put S1, which is G12, S2, which is 3H, I10, J22. Let me put I and J equal so we could see what happens with the branch. So let me make it, both of them, let's say 10. I guess I've talked about load immediate before. Load immediate is not a real instruction in MIPS, but it is a pseudo instruction. If I write it like that, then the assembler will use or immediate for this. Did I tell you before? I guess I told you before. Okay. So look at this here. S1 is 12, S2 is 3, S3 is 10, S4 is 10, I and J are 10, G and H are 12 and 3. So either we have to subtract G and H, or either we have to add them together. It depends on the values of I and J. We have either, if I and J are equal, then we do what? If they are equal, then we add. If they are not equal, then we subtract. Okay, let's execute this program. F2. F2 is a step into here. F2. Oh, I didn't compile it. Let's compile it first. Compile. Okay, compile succeeded. And now you could see the code. So F2, it starts from our main. So this is the first line of our program, which is load immediate S1 with 12. Okay. So look at the left side of the registers. After executing this instruction, S1 should be 12. 12 is C. So look at the left side. I press F2, so it has been executed, and S1 is now C. Did you see? Yeah, that didn't. I don't have the pointer to show you, so I show it here. Here in the register side, S1 now is C. Why it is C? Because we have executed load S1 with 12. Yes?
So if we were to actually have to write this in machine code, would we have to use the hexadecimal number?
No, if you don't put 0x, it considers it as decimal. The default is decimal. If you put 0x something, then it is hexadecimal.
Gotcha.
Yeah.
Press the control button on the keyboard and then roll out.
Yes, we could. And this is a step over, which we will see.
I mean the screen.
Yeah.
Could you press the control button on your keyboard and then roll off your mouse?
Oh, you want to zoom it up? Oh, okay. So you tell me just zoom up, then let's see if it works. Yeah, okay. I thought you are talking about Control F2, because there is something which is Control F2 here and F2. We will talk about Control F2 later. So now it is good somehow, but it is bad because you can't see the register file, all of them. And another thing that you should notice here is PC. What is PC now? How much? 14. So this is the location of the memory which would be the next instruction to be executed. Let's see. Here you see, these are the addresses. Here you see here, 0, 4, 8, C, 10, 14, 18, 1C, 20. So now we are at location 14. Our PC is 14. So if I press F2 now, then it means that the instruction at location 14, which is the PC, should be executed. You see it here. It is highlighted. In our simulator, it is highlighted, so you know that this instruction will be executed next. Yes?
Sorry, why does it go to location 14?
It started from somewhere and then filled one by one. For example, here, it started from location 4. Here, you see, 4 something. Then the next one, no, this is something. Here, let me show you from main. From main is okay. Yeah, okay. No, sorry. 0, then 4, then 8, then C, then 10. You see? So I started from 0. This is the location. I made mistake. This is not the location. This is the opcode. This is the location. Location 0 is the first instruction. That's it. Then the next instruction is location 4. The next. So with this program, you see our code, this one, load immediate something, is now at location 14. And we just started from location 0 and came one by one. What are these things before main? I am not talking about them right now, because for the computer to run your program, OS operating system loads them in memory, puts some kind of housekeeping code there, and then prepares everything for you. And here in this simulator, you see it has prepared everything and just gave you a main label. So you write your code in the main part, and somewhere it has a jump main here, you see? Jump main, and jump and link. I will talk about it later. Okay.
So as long as the address is a multiple of 2, it's okay?
Multiple of 4.
Multiple of 4? So how come you were able to do 10 at that one spot for the address?
10? No, 10 hex. 10 hex.
Oh,
10 hex is 16.
got you, okay.
Okay. And I didn't put this the addresses. I just wrote my program. The compiler compiled it and loaded in memory in this location. So this is something that compiler did. I didn't have any kind of role in it. So it's just did something. Yes.
Could we do it the other way around? Instead of branch not equal,
Of
do
course.
branch equal?
Of course, yeah. We could do branch equal, and then at the branch taken, we add them, and then we at the branch that the next instruction subtract. Of course, I told you it is not unique, so you could write something else. Yes, please.
Sorry.
Yeah. Okay. Yeah. The other. Yes. I knew your name. What was your name? Yeah, but I don't remember. My memory is very bad. Jacob. Okay.
The else, is that on just a label? Which
It is just label. That shouldn't confuse you. That okay, it is the else like the C program. Let me put something else. Instead of else, I put other, and here also I put other. This is a label. I mean other pass. Okay, so now I compile it. Is it successful? Yes, successful. So this is my new program. And the program exactly the same as before because we didn't change anything. You just changed the label. So it's exactly the same as before.
you can name it the label anything.
Anything. Just accept the instructions. Yes, so you cannot name it and.
Can we put our value in the start?
In what?
Start.
In a start?
Yeah, start.
A start. Where is a start?
Like above main.
Huh?
Like above main. He's talking
The
about.
main. Oh yeah, you could. Because it starts from a start. But the recommendation of this simulator is that you write your own code as main. But it starts from the start. So even if I could write here, load immediate S5 with something, and then jump to main.
Will it come across local and global?
Yes. So we don't talk about this right now.
One last question. It's a V0.
V?
In the start,
Oh, V0. We will talk about them. This is a register, and it represents a value that we return. Okay, we will talk about it later. I don't talk it later. So where were we? Okay, we were executing. Let's execute again. So again, I and J are equal. So we expect that. Did I compile? Yes. So F2. So it goes to here. S1 gets 12. S2 gets 3. S3 gets 10. S4 gets 10. If you look at the register file, S4 after executing that, do you see S4? S4 is 0 now. If I execute this instruction, S2, S4 becomes 10. Look at that. S4 is now 10. So S4 is 10, S3 is 10. So the next instructions is branch not equal S3 and S4 and going to another location. And S3 and S4, they are equal. So this branch is not taken. So it goes to the next instruction. Let me press F2. Look what happens. Came to the next instruction. The next instruction is add. The path of equal, I and j, if they are equal, then we add them. We add g and h, we add them, and then we put the add to f. F gets g plus h. This is that. S1 and S2 are g and h. F is S0. So this is the... And now, look at here. I just brought this to show you. If I press F2, right now the PC is 28. Look at the PC. Let me show you here. PC is 28. And the 28 is going to be executed. And then PC gets incremented by 4. So it becomes 2C. Okay, so let me press F2. So now S0 got the sum of those two. But PC now is 2C. PC, and the 2C is sub. So our F is overwritten. So the F is now the subtract of that. It is not correct. I wanted to show you. So let me correct it. To correct it, we come here, we put this. So after add, you go to the exit, not going to the next instruction that we wanted to come here if they are not equal. So go to the exit. Now everything is okay. So now let me run it with two numbers which are not equal, which makes the branch taken. Let me put I as 15. Okay, so I is 15, J is 10, so they are not equal. So branch not equal should be taken, so it goes to the sub. Let's see. Compile. Oh, why it's taking time? What happened? Huh? What happened? Oh, okay. Okay, compile. So let's execute it. Loading S1, S2, S3, S4. Here, branch are not equal S3 and S4. What is S3? S3 is now F, and S4 is A. One of them was 10, one of them was 15, so they are not equal. So executing these instructions means that the branch is taken, so it goes to the other location. Now it's not a bad time to look at the immediate value. I told you, this is an I format. The I format has opcode, 2 registers, and then immediate value, a 16-bit signed immediate value. What is this 16-bit immediate value? If you look at here, the 16-bit immediate value is, do you see that? The instruction is 167400003. Oh, somebody is connected. Okay. This is the instruction. So the instruction has, the instruction has opcode, 2 registers which are 16 bits, and then the immediate value. What is the immediate value here? 16 bits. You could see it. 167400003. 16 bits. You make 16 bits from that. 16 bits means 4 digits. 4 digits is what? These 4 digits. 0003. So this instruction, the immediate value in this instruction is 3. Okay. So if the immediate value of this instruction is 3, it means that if the branch is taken, then you have to add 3 to the PC. 3 means 12. Don't forget, because every location is should be divided by 4, divisible by 4. So 3 means 12. So you should add 12 to the location of the next PC to go to the place that you want. Look at here. The location of the next PC is 24, the next PC after the branch. And we have to add 12 to that. 12 means C, yeah? 12, it was 3, yeah? Yes, it was 3. So 3 times 4 is C. So C plus 24 is how much? 4 plus 12 is 16. So it is exactly 30. 24 plus C is 30. Nobody follows? 3, yeah, let me write here. 24 plus C. Write it for you, let me make it decimal so you understand it. 24 plus C in hexadecimal. If I make it decimal so you understand better. 24 is 2 times 16 is 32 plus 4 is 36 plus C is 12. So the result is 48. So we should go to the location 48, which in hexadecimal would be C. 30. Okay. Look at here. Now it's getting more exciting. So location 30, where is it? Here. Here is location 30. Location 30 is our sub. So the label other that we had put is location sub. So the compiler calculated that this is the branch. And from here, we want to jump here. And the branch should be relative address, offset. And the address, the next PC is here. So we have to add 3 times 4 to this PC, which becomes, here in our case, becomes 30. And this is here. So if I press F2 now, we go to that location. Look at that. So we are now at sub. And this is going to be executed and it is subtracted. And then the next of the rest of the program. Okay? Anything? Okay. So this was an example of an assembly code. So before going further, let's do the quiz. Yes.
Well, what happens if you don't type in exit? What if you don't have an exit command? Or is it
We don't. I told you all of the commands. Was there any exit?
There was an exit in the compiler in the simulator. I think at the very bottom.
No, it's the label. It's the label. No, it's not a command. It's a label. Here. This is.
Oh, so it's okay. So it just automatically ends once there's nothing left.
No, the processor doesn't go to the sleep. It always works. So whatever PC is, it gets that PC, the location of the PC, it reads the instruction, executes it, and then go to the next PC, go to the next PC, go to the next PC. So it never sleeps. It's always working. So what do? We just, maybe if there is something that you would like to end, maybe you just put a jump to the same location so the PC gets looped again. So let's do our quiz, which is very challenging quiz right now.
Times 2 speed.
Yeah, challenging, very challenging. So it takes you 1 minute, which I want you to all of you do it right now. I have to. It's called attendance. The quiz is called attendance. So I go there and make the end date, the end time, quiz setup. Okay, please go it now so we do it very fast and then continue our lecture. It's very slow today.
It's already over.
What happened?
We can go into the quiz.
Could you go to quiz right now? I don't need to set up.
I can see it, but I can't get in.
You set the availability to 3,000.
Yes, that's what I want to to make it. Okay, so we continue and then coming back later to when it is coming. It's very slow today. I don't know why. Okay, so let's continue. The next example. In the next example, we are going to have a while. While it is a C program. While save the ith array element of save. Save is an array. Is k, then be in the while and just add the I. And if it is not, then the while is finished and it comes out. Okay? Anybody here? Everybody here? Yeah. I will change the quiz later. Okay, yeah, it's come. 3:30, so I make it 3:50. Please. 50. Okay. I guess you have now. And the password is 0605. 5 of June. 0605. Okay, please, now try it. Very difficult question, and you should answer it very carefully. You were all here from the beginning, so you just put the same. So if somebody is left or somebody is now looking at from the home, you gave them signal to come to quiz, so that person should fill the fourth one. I hope that you don't give them the quiz password. Just this is for you, not for them.
I don't know, man. This is pretty difficult. I'm not gonna lie.
Guys, like, wait,
Am I really?
So did you pass the quiz?
you get our exit one.
Very good. Let's come back. Okay. Where were we here? So how should I write the assembly for this code?
Oh my God.
Everybody, please pay attention. In this example, we need also to go to the memory location and load the value of save. Save is an array in the memory, and then compare it with k, and then if they are equal, then we will be in the while, and we increment I. If not, then the while is finished and we are coming up. And now you can see here, let's say I is in S3, K in is S5, and address of the save, the first location of save in is S6. So this would be the base address, and we offset it by I. And again, remember, this is 32 bits. The values are 32 bits. So we should increment every time. We should go to, we should increment I by, we should multiply I by 4 and go to find the memory location. Did you get what I told? Because this save, the elements of this array, each one of them are 32 bits. So save 0 is at location, let's say S6. Then save 1 is at the location of S6 plus 4. Save 2 is at the location of S6 plus 8, and so on. So what do I wrote here? There might be some new instructions that I am going to introduce to you, and you learn this by doing something here. The first one is shift. Did I tell you about shift before? No, we didn't see. We saw. Yeah, I guess we saw that shift. Shift logical left. Shift left logical. SLL. Why do we use shift? Because we would like to multiply by 4. Multiplication by 4 means shifting left 2 times, 2 bits. So first, S3 is I. S3 is I. S3 is I. So we multiply I by 4. Okay. Then we have to find the address. The address would be, the base address is S6, and we have to add the offset of the number that I times 4 to that. So I times 4 is here, so we add T1 to S6 and we get T1. So T1 is the memory location of element save I, okay? Is the memory location of S save I. And now we have to go and load from the memory from this location the value and put it somewhere. For example, here we put it in T0. Look at the next instruction. Load word, load from the memory. Which address we load? We load from the address T1 as a base and offset of 0. Okay? This is the location that we have put there. Then, okay, now we loaded save I, and we have K also in S5, so we have to compare these together. If they are equal, then we go to the next array element. It gets I plus 1. If they are not equal, the loop is finished, the while is finished, and we are. So we compare T0, which is save I, the ith element of save, with S5. What was S5? S5 was K. So we compare them together. If they are not equal, we jump to exit. If they are equal, we go to the next instruction, which we are actually doing increment of I. So add I, S3, 1. S3 plus 1 goes to S3. So I increments by 1. And then go back again. The next thing. So we have updated I here. So I got incremented. Then again, multiplication by 4, comparing, finding the location of the element of save I, and then loading, and then comparing, and again, the same. So this is the one that we have it there. Okay. You could put it in the assemblers to see how it works. The simulator. This is something that just give you a basic block is a location, a set of code which no embedded branch except at the end, so it doesn't leave the block only at the end. It doesn't look, and nothing is coming into the block only unless at the beginning. So it means that this code always be executed one by one. This one, then 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 this one. So this is a basic block. So what? So if we found a basic block, what to do with it? When you have a basic block, then it means that these instructions are going to be executed for sure one by one. So if the compiler wants to do some enhancement, wants to do some kind of optimization of the execution of the code, it can, please be here. It can, what happened? There is a riot over there. Do you need my help?
Sorry.
Anything that I could help? Okay. So if the compiler wants to, for example, switches this instruction with this one. So it makes it easier to be executed. You don't have any idea right now what does it mean but just think about it. If you have a code which you are sure that one by one they are going to be executed, then you can do something with these instructions, changing, putting something there. But if you have a code that, for example, here is a branch, it goes somewhere else. So you cannot, for example, bring this instruction to the top because it might not be executed at all, because we might reach this branch and it goes out, and this instruction never being executed. So if it is a basic block, then compiler could work on that, and it's good. A compiler identifies basic blocks for optimization and so on. So I guess that's it for now, and we will continue. Hopefully I could try to finish this slide, this set up slides for. You have the slides in the site, so you download it and look at that.
We've 4 hours.